Next topic of power system optimization and AI implementation, AI applications rather. Yeah, in the last class we were discussing about a lot of linear programming, simplex method, graphical method, and all. Moving ahead, we are getting into the core real-time analogy of this power system optimization and AI applications. With respect to, today we'll be discussing about non-linear programming, dynamic programming, load flow analysis, and a bit of intro to optimal power flow as well. So today we move beyond the linear optimization framework developed in the previous session there and begin working with mathematical forms that occurs naturally in real power systems. So the central theme is that the further we move towards the actual physical systems, the less appropriate a purely linear description becomes, right? We come across with abnormalities, contingencies on a real-time power system. So we'll begin with this with a non-linear programming and see how the exact generator cost curve can be optimized without precise linear approximation, one thing. And then we move to dynamic programming where the important issue is not simply non-linearity but decisions that involve from one stage to another. So after that, we return to the electrical network system through load flow analysis and determine the actual voltage magnitude, voltage angles, line flows. So finally, these ideas come together in optimal power flow where economic objectives and physical AC network equations are solved simultaneously. So if you want me to have a quick recap, that is a bridging session from last class to this class. See, let's first connect to today's session with the previous one. Linear programming gave us a very useful framework because both objectives and constraints were linear there. However, real generator cost curve are normally curved, right? And full AC network equation contains voltage, products, and trigonometric terms. In the previous formulation, we therefore had to simplify or linearize some of the relationships. That simplification is useful, but it is still an approximation, right? Today we remove that restriction because nonlinear programming allows the original curved cost function and nonlinear constraints to remove in the mathematical model. See, we will also extend our thinking from a single operating point to decision over time through dynamic programming, load flow analysis, dynamic programming basically. Then we can switch to load flow when then tell us what network physically does, and ACOPF brings the economic and electrical descriptions together. So this is the overview of where we are heading towards. So you can see here there is a roadmap. We have four connected parts here. The first part is nonlinear programming where we will develop the Lagrange multiplier and KKT conditions and apply them to the quadratic equations, quadratic economic dispatch problems. The second part is dynamic programming where we will look at sequential decision and Bellman's principle of optimality. The third part is load flow analysis. Here the objectives changes. Rather than asking what generation should be selected, we calculate the electrical state produced by the specified generation. Someone wants to join. Yeah. So the fourth part is optimal power flow. This is where the cost function, generator limits, and actual AC network equations becomes one constrained nonlinear optimization problem for us. So what you can expect from this session by the end of the session? The important result is not simply that several algorithms has been introduced. The goal is to understand the relationship between them. So we should be able to formulate a nonlinear optimization problem. One thing, use Lagrange multiplier. Second thing, KKT conditions. Third thing, and interpret the multiplier economically. So we should also be comfortable with the state-state decision, state-state decisions, decision structure of dynamic programming, the classification of slack, PV and PQ buses, the nonlinear AC power flow equations, right? Finally, we should be able to look at an AC OPF formulation and identify the economic objectives the network equality constraints, and engineering inequality constraints too. So, uh, hope the recap was useful and you people remember what we discussed in the previous class. Excuse me. Hello. Uday, what I want is uh, what did you learn from the last two classes? I mean, if not the entire script, I really want every one of you who are here to leave your comments in the comment box. Okay? Because I think most of you have switched on and have left the class, I guess. Please do that. Well, I'll start with the non-linear programming because I can't waste much time here. See, we know being a means now at part one we shall start with the non-linear programming. This is the simplest way to understand non-linear programming is to remember the restrictions that defined in the linear programming. What was that? Everything had to be linear there. Once the restriction is removed, the same thing, the objectives or constraints can contain squares, products, ratios, exponential functions, trigonometric functions, and many other nonlinear relationships. See, this is important in power system because nonlinear behavior is not an artificial complication. The quadratic generation cost curve is nonlinear and the AC power flow equations are nonlinear because they arise from interactions of voltage magnitude, current and phase angles. So nonlinear programming therefore gives us a mathematical framework that is much closer to actual engineering systems. So when you look into a nonlinear programming, see consider a typical generator cost function that we discussed in our much prior classes of having an equation of Fi Pgi is equal to Ai Pgi square. Hope you remember that. So the quadratic form, the quadratic term means that the marginal cost change as generator output changes. So if we approximate the curve using a straight line segments, we make the problem easier to solve, but we also introduce approximation errors here. Like uh, an NLP allows us to retain the original curve, the price we pay in mathematical complexity. A general nonlinear objective need not to be convex, okay, and it also may contain several local minima. So an iterative algorithm can therefore find a point that is locally optimal without proving that it is global optimum. So this is the fundamental trade-off. So the better representation of the physical problem, but a more difficult optimization landscape here. Okay. Well, moving ahead, see before considering constraints, we begin with the unconstrained. Good. I don't think anybody else is here.
So previous one classes.
So before we begin with an unconstrained optimization, suppose a smooth function has a local minima. Okay, at the bottom of the curve, the slope is 0. This gives the first order necessary condition for us. Anyways, you have your df by dx is equal to 0, right? So for several variables, the equivalent statement is gradient. The equivalent statement is that the gradient is 0. However, a stationary point is not automatically a minimum. It may also be maximum for a saddle point there. See, we therefore examine the second order behavior also. For a single variable, a positive, sorry. So, for a single variable, a positive second derivative indicates upward curvature and a local minimum as well. In several variables, the Hessian matrix provides the corresponding curvature information. So, if you look into the function of several variable df by dx1, I'll just choose the pen here. Yeah. So this df by I'm sorry, that all could have came together, man. Yeah, yeah. So dou f by dou x is equal to dou f by dou x2. This keeps on. That will be equal to 0 then. Fine. So we can have one worked example for an unconstrained minimization. Consider the cost of FP already been given here, the equation, right? And it is a genuine minimum. Fine. So, so differentiating this entire equation, what you get df by dpeg, if you differentiate this equation, okay, you get df by dpeg is equal to 0.012 pg into plus 1 minus 1.8. So here we are differentiating the cost function once with respect to pg. Okay, so the first order condition we need to set is 0, right? Therefore what shall we do? This entire equation we will set it to 0. So apply this first order equation. Here the second derivative is positive. Therefore, the stationary point is genuine minimum. This simple example established the basic nonlinear optimization pattern. uh, Formulate the objective and obtain the first order condition. So calculate the candidate solution and then verify with the local curvature here. As you can see, once we are done with the differentiation, we are setting it to 0, right? The slope must be exactly 0 at stationary point and then solve algebraically for PG. PG is equal to uh, algebraically for PG. This is the candidate stationary point. So if you just try to equate for PG here, okay, sending 1.2 other ways and you will get 1.8 divided by 0.012, you will get 150. Therefore, d square f, that is the second order differentiation, d square f by dpg square is equal to 0.012 greater than 0. So check the second order condition also. The second order derivative is positive constant again, confirming this is a genuine minimum curve. The curve is convex everywhere. So Pg is equal to 150 megawatt. We got it from here. Is a confirmed minimum since the second order differentiation is also positive constant for all power generations here. So when we look into the next part, that is nonlinear programming, that is constrained NLP. Give me 1 second. See, what happens with a constrained NLP? See, in a real power system optimization, uh, they are all constrained. So unconstrained calculation is only the starting point. See, in economic dispatch, for example, when the generator outputs must add up to the required demand, increasing one generator while keeping demand fixed necessarily affects another generator. For a problem minimizing effects, subject to G, I mean, if you want to minimize, I mean, any problem, numerical, I mean, fx, if you are trying to minimize, subject to gx is equal to what? It should be 0. So the Lagrange method constructs, I think I have given the Lagrange method as well here. You can see here. This Lagrange method, what it do, it actually constructs L, x and lambda, right, is equal to f of x lambda g of x. So the constraint is therefore incorporated into one combined function. At the optimum, the derivative of Lagrange with respect to the decision, uh, I mean decision variable and the multiplier, they must satisfy the stationary conditions. The multiplier also has an important economic meaning. It measures the marginal value associated with constraints. See, at the constant optimum, the objective's rate of change and the constraint's rate of change must point in exactly the same or opposite direction. So lambda measures the exchange rate between them. Setting every partial derivatives of L to 0, that is, kind of, here it is, dl by dx is equal to 0 and dl by dm lambda is equal to 0 gives exactly enough equations to solve for both x and lambda simultaneously. But lambda is not just bookkeeping here. Okay, lambda is a real physical meaning. It measures how much the optimal objective value would change if the constraints right hand side were relaxed by 1 unit. Exactly the shadow price idea, what we try to discuss in the second session. uh, you have the duality discussions as well. So that is where the lambda will pitches in. Okay, then moving ahead, solving the stationary condition. See, for two variables and one equality constraint, the Lagrange Lagrange will produce you three equations. In three unknowns, the two decision variables and the multiplier. So differentiating with respect to each decision variable produces two marginal conditions, while differentiation with respect to lambda returns the original constraint for us. See, when these equations are rearranged, see here itself you have three different equations. I've already displayed it here, x1, x2 and lambda. And here you can see equation 1, equation 2 and equation 3 simply returns to their original constraints here, right? So when these equations are rearranged, the rate of change of the objective per unit change in the constraint becomes identical for the decision variables. Therefore, in economic dispatch, the constraint is power balance. Since one additional megawatt, so uh, since one additional megawatt for any unconstrained generator contributes 1 megawatt to the balance, the result becomes equality of marginal generation costs. This is mathematical origin of equal incremental cost rule for us. Well, so for problem minimize, f of x1 is subject to, here f of x1 is subject to g of x1 and x2, which is equal to 0 there. So the Lagrange L is equal to f lambda g gives exactly three equations and three unknowns as mentioned, right? Therefore, Nonlinear programming is aiding us to deal with the non-constraints as well. If you just want to know nonlinear programming, we now apply the Lagrange formulation to the actual quadratic equation dispatch numerical here. Okay, so the two generator costs are, you have the two generator costs. One is f of pg1 and then you got f of pg2, right? So while the total demand is 300 megawatt, the Lagrange is constructed by adding the power balance constraints to the generator costs. See, differentiating with respect to PG1 will gives us, I think, where we have the differentiation. First and foremost, we are trying to have the Lagrange objective of the power balance equality constraint. You can see here L is equal to FPG1 plus FPG2. That is these two things plus this is what I was telling you, that Lagrange is constructed by adding power balance constraints. This is the power balance constraint between the two equations, the demand minus generated. Okay, whatever is left over will be the excess if we get negative. If we get positive, that means that demand is more there, right? So when you try to differentiate this equation, dl by dou L by dou Pg1, okay, you are differentiating with respect to Pg1 first, so you get this equation. So that is, this is a partial derivation. So this partial derivation to 0 for generator 1 gives us the marginal cost value and lambda condition as well. Similarly, you have the for generator 2 also. Not every generator's marginal cost is same lambda at the optimum there. Okay, therefore, see, solving these two together will give us Pg1 plus Pg2 is equal to 300. Approximately, it gives us the lambda value of 7.63. If you solve these two equations, okay, Pg1 is equal to lambda minus 6. When you solve this equation, lambda minus 6 divided by 0.012 will give you the Pg1. Similarly, Pg2. When you solve these two equations, Pg1 plus Pg2 is equal to 300, because that is what the demand is all about. It is been given in the question, right? Therefore, now if you solve for lambda, okay, so you get a lambda approximately equal to 7.63. This lambda is nothing but, okay, yeah, this lambda is nothing but your cost per megawatt hour. Okay, so moving ahead, excuse me. So the total cost is approximately 2,342 rupees. Cost unit, if you want to be precise, it is 2,342.14 rupees. Yeah. The important result is that the true quadratic functions have been optimized directly. No precise linear approximation is required. L F1 Pg1 and F2 Pg2 plus lambda PDG1 minus Pg2. All these equations have been given there, right? So this is the same condition for your generator 2 also. This is how we have obtained to the solution of operating cost, the total cost and everything by using two generators. If we still continue with the nonlinear programming, the value of the lambda, what I'm trying to do is interpreting the lambda here, what exactly it is. So has a physical interpretation. It represents the marginal cost there at the current optimal dispatch. If demand increases by a very if demand increases by a very small amount, the additional generation must be obtained at approximately this marginal cost. See, provided the same set of constraints remain active. Okay. So both generators have the same marginal cost at the unconstrained optimum. If one had higher marginal cost than the other and both were free to move, then generator could be shifted towards the cheaper marginal units and the cost would fall there, right? Therefore, equality of marginal cost is not just a mathematical curiosity. It is the economic condition for optimal allocation of the incremental generations. Thus, this same idea appears as a shadow price in LP duality and has the basis of classical lambda iteration methods. Moving ahead, adding inequality constraints. So, the larger multipliers methods handles equality constraints for us, but real generators also have inequality constraints. So, a generator may have a minimum and maximum output. A transmission line has a flow limit and bus voltage as an acceptable operating range, right? So, just to mention, as I have mentioned here, the Karush-Kuhn-Tucker, that is a condition that is called KKT, extend the Lagrange's framework to these inequalities. They include stationarity, primal feasibility, dual feasibility, and complete slackness. Complementary slackness is particularly useful because it mathematically distinguishes an active constraints from slack constraint. Okay, when an inequality is inactive, its multiplier is zero. When the constraint is binding, its multiplier may become non-zero and influences the optimum there. So you can just see by means of equation also, this was our original function f of g or f of x at this point of time. We included a lambda functionality. Now for the inequality constraints, we are including one more KKT, KKT condition where it extends our Lagrange equation by mu is in mu times hx, where mu is the KKT multiplier for the inequality constraint, where h of x is not less than or equal to 0 there. Fine. So when you look into the stationary dou L by dou x, this entire differentiation is equal to 0. Same idea as the Lagrange condition what we discussed in the previous slide, isn't it? And you have primal feasibility, that is gx is equal to 0 and h of x is less than or equal to 0. The solution must actually satisfy every original constraints there because everything starts from the 0, as you know that in the curve. And dual feasibility, mu is greater than or equal to 0, that is the inequality multiplier cannot be negative, it only pushes one way. So when you look at the complementary slackness, mu of h of x is equal to 0, either constraint is binding that h of x should be equal to 0 or its multiplier is mu itself is 0. Never both non-zero. Okay. Well, so this is worked example 3. When generator limit binds, okay. If you return to the previous economic dispatch solution where generator 1 was scheduled at 135.7 megawatt, suppose its true maximum is 120 megawatt. This question is an deviation from our this problem. Okay. Here, as you can see, at the answer, after finding out the lambda and what we found out is PG1 was 135.7 and PG2 was 164.3, right? This was the condition. I mean, this was the answer what we obtained. But now what are we doing now? We are trying to stretch the numerical furthermore. What are we going to do? Generator 1, here it had 135.7 megawatt. Okay. This, what are we going to do? Mandatorily, we are trying to bring it down to 120 megawatt. As per the question says. Right? We are trying to reduce it. See, the unconstrained optimum is now infeasible because it violates the physical limits there. The upper limit therefore becomes active. Generator 1 is fixed at 120 megawatt, right, with a 300 megawatt of demand as usual. Okay. And now generator 2 must provide the remaining 180 megawatt. If that value is within its own limit, the dispatch is feasible. But you know that PG2, I mean the upper limit therefore becomes active and generator 1 is fixed to 120 now. So notice that equal incremental cost condition is now modified, right? Generator 1 is not free to increase its output anymore because it's already running with its full maximum of 120 megawatt. So its marginal cost need not equal the system lambda here. Equal incremental cost applies to the generator that remains unconstrained and free to adjust their output. Therefore, if you if you look into this after knowing all this theory part, see check feasibility of unconstrained solution. That is 135.7 megawatt will violate this 120 megawatt now because new peak demand is 120 megawatt. Previously it was 200 megawatt, right? The constraint is violated, so that solution is no longer valid for us. So apply the complementary slackness, assume this limit binds. If pg1 is equal to 120 exactly, that is binding, okay, then mu should be greater than 0 is allowed. We simply fix pg1 is equal to 120 and resolve for the rest. Remaining demand for generator 2. As you can see, 300 was the total demand, 120 is met by generator 1. So generator 2 should meet 180 megawatt now, right? It should cover up for all remaining demands. So check for generator 2's own limit. PG2 has maximum of 200, no problem. Then 180 is lesser than or equal to 200, of course it is. Then it is feasible. This is a valid candidate solution. You can easily run your generator. Now what is happening? You are running PG1 at its maximum potential, that is 120 megawatt at its maximum limit, and now you are pushing your generator 2 to 180 megawatt, which was in 160 or something in the previous case, right? So generator 1's binding limit means its marginal cost no longer equals lambda there. The equal incremental cost rule only applies to unconstrained generators, that is non-binding generators. So now let's have a look into the gradient based approach or method. See, for small problems we can sometimes solve the nonlinear optimal equation algebraically, but in real optimization problems are much larger for us. So numerical iterative methods become very necessary. When we talk about the gradient based methods or gradient descents, they provide the simplest picture. The gradient points towards the direction of greatest local increase. So a minimization algorithm moves against the gradient according to the x nu. Okay. So x nu is equal to, we have a formula for it, I think. It's not given here. Here it is. So the step size control the distance moved at each iterations. So Newton methods uses the curvature information as well, allowing a more informed corrections. This gives us faster local convergence, but requires more computation. So the fundamental caution remains that non-linear solver can converge to a local optimum when the problem is non-convex. That is the important thing. This you can read out. See, the small statements I have provided you in the PPTs at the bottom is for your further understanding and will really help you out to conclude your concept and ideology. So, because of general NLP feasible region, the objective need not to be convex here. Gradient-based methods can converge to a local optimum. That is not the true global optimum, right? So, the price of removing linear programs linearity guarantee flag at the start of this part, right? Well, see, nonlinear programming method appears in many power system applications. True economic dispatch is one example because generator cost curves can be represented directly rather than piecewise linearly. Alternating current optimal power flow is another because the AC network equations are non-linear. State estimation can involve uh, non-linear least square formulations, voltage and reactive power optimization also contains non-linear relationships. Hydrothermal coordinations can become non-linear because reservoir storage, water release and generations are linked over time. Short circuit and stability calculations likewise involves nonlinear electrical relationships. The common theme is that nonlinear programming is not merely a mathematical abstraction. It is a framework for representing engineering relationships that cannot be captured adequately by straight lines. So, this we can come to an end of nonlinear programming. We can condense the first part can be condensed into few connected ideas. That is, NLP will remove the linearity restrictions, Lagrange multipliers handles equality constraints, while KKT conditions extend the formulation to inequality constraints. This is pretty understanding, I guess, right? Here, linear programming has only this functionality. When it comes to nonlinear programming, we will be having Lagrange component involved as well. So Lagrange equation will be f of x plus lambda g of x. When it comes to the KKT condition, it will have extra mu character being injected here. Fine. So, but moving ahead, if you look into the economic dispatch, it gives the important result that every unconstrained generator has marginal cost equal to the system lambda. When a generator limit becomes active, the generator is no longer free to move and simply uh, and the simple equality continues must be interpreted through KKT conditions. So for larger problems, numerically iterative methods are required, and in convex problems, numerical convergence does not automatically establish a global optimality here. So let's move towards the next part, that is dynamic programming. See, the main change is that we are no longer dealing only with the mathematical shape of an objective function. We are dealing with a decision that unfolds through several stages. Generator commitment is an excellent example. A unit that is switched on in 1 hour may have to remain on for several hours because of the minimum uptime, right? A unit that is switched off may have a minimum downtime. Startup costs also mean that the decision in 1 hour affects the economic consequences of future decisions. Therefore, dynamic programming handles this structure by describing the problem through stages, states, and decisions, rather than treating the entire sequence as one undifferentiated optimization. So if you want to know what is dynamic programming and why do we need it, see every technique so far, what we have studied, linear programming, non-linear programming, they find the best value of a set of variables all at once in a single simulation decision, in a single simultaneous decision. Many real problems, though, unfold a sequence of decision over time or stages, which generates to commit this hour or next hour and the hour after. So each choice affecting what is possible later. So dynamic programming was again developed by, not again, it was developed by Richard Bellman in the 1950s. It built specifically for these multi-stage decision problems rather than optimizing all decisions simultaneously. So dynamic programming basically it breaks the problems into stages, often exactly to be precise in time stages or time periods, and states also the situation at each state. Example, which units are currently on. Then solve a much smaller optimization problem at each stage, working through the stages in sequences. So we can say that dynamic programming was built or developed to handle multi-stage decision problems. A stage often here it represents a time period, while the state represents the conditions of the system at that stage. Therefore, the decision determines how the system moves to a new state. But the important requirement is that the current state must contain enough information about the past to determine the future problem. If unit commitment, in unit commitment, the current on-off status and other necessary commitment information can define the state. So dynamic programming does not require the problem to be linear. Its defining feature is a sequential structure and ability to represent the future through well-defined state. As you can see there, the conclusive statement I have given you, it doesn't require it to be linear or even continuous. Its only requirement is that the problem can be broken into stages with a well-defined state, summarizing everything for earlier stages that matters for later decisions. Now we shall have a brief look into Bellman's principle of optimality. So, Bellman's principle of optimality is a central idea of dynamic programming. Once a particular state that has been reached, the best remaining decisions must form an optimal policy for that state. So the algorithm therefore does not need to reconsider every detail of history that led to that state. The Bellman's recursion expresses this through a value function here. The value function represents the best achievable cost from the current state and stage onward. The recursion combines the cost of presentation with the best cost to go from the resulting state. This is what turns a large sequential optimization problem into a collection of smaller problems and that can be solved recursively and reused. So this equation will give you the entire understanding. V state and V stage minimum cost decision plus V new state and next stage. So this is how the Bellman's recursion operate. It's a mathematical heart of the DP programming. So when you look into the V state and V stage is the optimal cost to go, the best possible total cost achievable from this state at this stage onward to the end of the problem. So the recursive formula, today's decision cost plus best possible cost of everything after is what DB break one huge problem into small ones. So as you can see here, you got four stages. This is stage 0, this is stage 1, this is stage 2, and this is stage 3. You got 4 stages here, right? The stagecoach problem provides here provides a classic, I mean, a simple way to see the Bellman idea without complexity of the power system. See, the objective is to find the least cost route from A to F. Okay, you got multiple ways there. A brute force method could enumerate complete routes. Dynamic programming instead work backward from destination. Okay, it calculates the best cost to go from each intermediate node, and also it reuses the result whenever the node appears again. So the important lesson is not the route itself here. The lesson is that repeated sub problems do not need to be solved repeatedly. So starting at the last stage, uh, this is called backward recursion. So here, starting at the last stage, the cost from D to F and cost from E to F is 6. You can see D to F and E to F. D to F is 5 and E to F is 6. The route through D costs 7 plus 5. So if you come through D, it will cost you 7 plus 5. Okay. Therefore, the total cost will be 12, while the route through E cost uh, for B, okay, cost you 4 plus 6. That cost you 10. Therefore, the best cost from B is 10. Okay, to F, you'll come from here, you'll have 2 extra here. This 2 is common, you can't eliminate, right? Then you come to B, then you come to E through B from root 4, and then you go to F from 6. That costs you 12 rupees in total, or 10 rupees. When you think of calculating the route at from C, the cost through D costs you 3, right? Plus 5 is equal to 8, while the route through E will cost you 9 rupees. So the best cost is from C is 8 rupees, 8 units, or 8. Okay. Finally, from 8, the route through B costs 2 plus 7, that is 12 rupees, while the route from C will cost you 13 rupees. So the optimal path therefore is A, B, E, F with a total cost of 12 rupees. The calculation illustrates exactly how the Bellman recursion reuses previously solved problems. Okay, we compute the original cost to go, that is V node, starting from the last stage and working backward. Each node answers reuse nodes that are already solved. You can see here, V of D will give you 5, V of E, you can see here, will give you 6, VB here is minimum of 7 plus VD, as you can see here, minimum of 7 plus VD plus which is equal to plus 4VE plus 4VE. Well, so minimum you have 12 and 10. Okay, so 10 via E is your best route, E is the cheapest route. When you think the similarly with V of C, you have minimum of 3. Okay, this is inevitable, plus V of D, that is turning towards V of D now, plus 3, this is one more route, plus V of E. So you'll get it as 3 plus 5 3 plus 6. Minimum of 8 and 9. 8 via D, this route. C, D and F will cost you only 3 and 5 rupees. This will give you minimal values of 8 and 9. Therefore, 8 via D is the cheapest route. This is the possible power flow. This is the minimum what we can find out. So moving ahead, if you consider it from moving from A, okay, you have 2 here, and VB what it got you 10, right? So 12 via B still is the easiest way. Very similarly here also for C you have 5, right? And what was the optimal decision here? VC is equal to 8. 8 plus 5 you get 13. Sorry, 12. This is the backward recursion of Bellman's formula. I hope you understood this. Any doubts with this class?
Yes, sir. Yes.
You have doubt?
No, sir. No.
Others? Sneha, Rashmi, Sanjit, Mamta,
No
yeah, you
doubt,
wanna
sir.
speak? Mamta, clear?
Yes, sir.
Sneha, you are trying to speak
Yes,
something.
sir. Clear.
Moving ahead, I'll pause here. Okay. Uh, just give me 5 seconds or 5 minutes. I'll be back. Okay. We'll take a small break. Okay. Has. Hello. Bye. Well, we shall take it back. Hope your people are here.
Okay, sir. Yes, sir.
Just give me a second. So, uh, we will discuss about the unit commitment. Unit commitment. Anybody can briefly tell what is unit commitment? Unit commitment means committing one particular generator or a set of generators to deliver a particular load. Okay, this is having. I mean, this we will learn in tomorrow's or in the session 5 classes completely. Okay, so here the same structure can be transferred directly to unit commitment. Unit commitment. Yeah. Each hour becomes a stage here. Okay, the state is on and off combination of all generating units here. Okay, so the decision is the transition to the next commitment state. For example, if we have three generators, the state such as on, off, on tells us which units are committed during that hour. So the stage cost can contain the fuel cost of operating and committed unit as well as the startup cost associated with the changes in commitment. So the power system advantage is that a complete 24-hour schedule does not have to be treated as a completely independent object every time. So the algorithm can reuse the best cost to go associated with the state that have already been evaluated. Okay. So when you look into the weakness of dynamic programming, the major weakness of DP appears when the number of unit becomes large, with total possible commitment state of every unit. N unit produces to the power of n possible on-off combinations, right? 5 units gives you 32 states. 10 units gives you 1024 states, right? 20 units gives you approximately 1 million states, and 50 units will give you approximately 1.1 quadrillion. So the growth is exponential. This is a curse of dimensionality. It explains why classical dynamic programming become difficult for a large utility scale unit commitment problems, and why more sophisticated optimization, decomposition, approximation, and heuristic approaches are important in practical systems. So a real utility may commit decisions for hundreds of generating units here. Storing and evaluating every possible on-off combination at every hour is computationally impossible with the classical DP. This is precisely the motivation for the heuristic and AI-based methods. Generating algorithm, practical swarm optimization introduced that will be coming up in the next sessions. Okay. Now, if you look into the major aspect of, this gives you a very good understanding and clarity that how dynamic programming, linear programming, non-linear programming uh, should be understood as a tool for different mathematical structure. See, LP is suited to linear optimization. NLP handles non-linear relationships. Particularly, it continues variable and constraints. DP is designed around stages and states and can handle discrete as well as continuous decisions. When the problem has as required the sequential structure. In problems is in sorry in power system, LP can support linearized formulation such as DCOPF. It has been mentioned here, power system use, where NLP can be used for true economic dispatch, ACOPFs, while as uh, dynamic programming can be used for unit commitment. The methods therefore complement rather than simply replace one another. They have their own unique area to play rather than DP is replaced by LP or LP is replaced by NLP. Okay, they have their own unique way to play around. So what all we studied in this second part. The second part you can summarize through four words: stage, state, decision, transition. Therefore, Bellman's principle says that once the state is known, the optimal remaining policy depends on that state rather than on the entire past history. So, Bellman recursion combines the current decision cost with the optimal future cost. Unit commitment provides a direct power system application with hours as stages and commitment configuration as states. So the principal limitation of, the principal limitation is the curse of dimensionality because the number of states can grow exponentially with the number of units. So all those things we try to have a look. This recursion equation, this is very important equation. Please try to write it down. I can wait for 2 seconds or else anyways I'll share you the PPTs. The very important part, the next part is load flow analysis. So we now move into load flow analysis. See, economic dispatch tells us how much power should be generated, but it does not tell us what network voltage profile or line loading will be, right? See, we have already know how much power flows where. Load flow analysis answers the question. Those techniques load flow analysis answers the question those techniques take for granted. Like given a specific pattern of generation demand across a network, what are the actual voltage magnitudes and angles at every bus, and how much power flow on every line. So load flow answers a different questions here. It particularly patterns of generation and demand is imposed on the network. What are the actual voltage magnitudes? What are the phase angles at the buses? And what power flows through the transmission network? See, this network equation problem rather than an optimization problem. Its importance is enormous because voltage profiles, line flows, and losses must be known before we can judge whether a proposed operating point is physically feasible. Right? So optimal flow analysis is essentially building a block of everything else in this course here. So OPF again, if you come back in part 4, repeatedly runs the load flow like calculations while searching for optimal dispatch. Now we are concentrating on the dispatch, not on the generation. Please do understand. Load flow is sort of transmission distribution uh, point of view. Now, bus classification, every bus plays a different role. Every bus in the network has four quantities: voltage magnitude, modulus of V, voltage angle, delta, real power P, reactive power Q. Load flow always specifies exactly two of these per bus and solves for other two, which two are known depends on the bus type. So load flow analysis solves the steady state electrical equation of the network for a specified generation and demand pattern. There are no objective function in an ordinary load flow calculations. The task is to satisfy the physical equation. The result here includes bus voltage magnitudes, angles, generator reactive power, slack bus quantities, line flows, network losses. These quantities are essential for planning and operations, right? What is slack bus or a swing bus? I think you all know this, right? Slack bus or a swing bus? Uday?
Yes, sir. Yes.
So, Mamta, Uday, Rashmi, Salman, Sneha, Shivraj. Can anybody define me what is slack bus? I'm waiting for your answer. Please make it fast so that we can move. No? Okay. At least you can read from the PPT here. This is a reserve bus. This is the bus which will stand for any other bus. If there is any change in the voltage magnitude, if there is any higher voltage, that voltage will be absorbed. If there is any problem with the power factor, slack bus, swing bus comes into picture, right? Then you have generator bus or PV bus. You can also note that what is known in the slack bus, voltage magnitude is known, what how much voltage is put on the slack bus, and phase angle or else voltage angle is known. Both are fixed at one at an angle of 0 degree. This is a standard. Unknowns, real power and reactive power. PV bus known, real power and the voltage magnitude. Unknown, reactive power and the phase angle. So generator bus, a generator holds its voltage steady via automatic voltage regulations while its power output is scheduled. And then you got a PQ bus. What you know, real power and reactive power is known, voltage magnitude and phase angle is unknown, right? So this is where I really want you to look for. So moving ahead, see the distinction uh, is useful here. Economic dispatch asks what generation should be. Load flow asks what happens on the network for a given generation pattern. And OPF will combine those two questions, right? You can put those things on your book right now so that later you can easily understand when we come to the OPF. So to expand your understanding here, again, you have four basic quantities: P, Q, and voltage magnitude. And See, this slack bus is especially important for any power system because the specified generation on load values elsewhere do not normally account exactly for transmission losses. The slack bus absorbs the final active reactive mismatch required by the network solutions. So when you look into the power flow equations, AC power flow equation becomes non-linear because any answer why AC power flow become non-linear? Excuse me. The AC power flow equations are non-linear. Why? When you look into AC, it's a complex power. It depends upon both voltage and current, while current at one bus depends on the voltage at all connected buses, right? When the equations here are expressed in polar form, the real power equation contains the terminologies involving VI or PI and VJ or PJ, right? I mean, sorry, it's not P, it's VI and VJ. That is real voltage and the imaginary part which is basically from the reactive part, and cosine or sine function of the angle difference as well. The reactive power equations has the same nonlinear structure. This explains as why the full AC load flow problem cannot be handled by simplex algorithm of linear programming. The equation must be solved iteratively. The unknown depends upon the bus type, whether it's a PQ bus. PQ buses contributes to voltage, magnitude, and angles as unknowns, while PV buses normally contributes to voltage, angle, and reactive power as the quantities involved in the solution. So we have answered why non-linear because it contains a complex power. So you might be we will be having both voltage and the current as well. So why this matters? Because unlike in OPFCs or DC OPFs, the true equation cannot be solved by simplex or any LP method. We need the same iterative gradient style method to introduce NLPs. So the unknown to solve for at PQ bus you have V, and I think you can go back here at PQ bus. What are the unknowns? You have Q and uh, phase angle, right? At PV buses, delta and Q, and at slack bus P and Q. Everything else is specified data. So one such approach, I think you have studied this. One such approach of load flow analysis is Gauss-Seidel. This is a classic iterative load flow method. The unknown bus voltage is isolated from the relevant equation here, right? And the buses are then updated sequentially. A common initialization is a flat start with voltage magnitude near 1.0 per unit and angle near 0. During each sweep, the latest available voltage values are used. After the sweep, the solution is checked for convergence. So the method is attractive because it is simple and inexpensive per iteration. Its main weakness is convergence speed. As the network becomes larger or more ill conditioned, the number of iterations can increase significantly. That will be a bit of headache for you. So, if you want me to repeat the procedure or the algorithm for the flowchart of this Gauss-Seidel method, okay. Initially, what we do, we guess every unknown bus voltages, commonly flat start, means V is equal to 1.0, delta is equal to 0 degree everywhere in the first iteration. So for each bus in turn, recompute its voltage from the power equation using the newest value for all other buses. Check convergence. This is important. Has every bus voltage changed by less than a small tolerance since the last full pass? Repeat or stop. If not converged, do another full pass. If converged, report the final voltage. So Gauss-Seidel is a simple to program and each iteration is computationally cheap. As I told you, it is having slow convergence. okay, often needing dozens or hundreds of iterations. As I told you, if you have any larger system or ill conditioned network, this is really going to, take off your entire time and space, everything. Very similarly, when we look up in solving iteratively the Newton-Raphson method, Newton-Raphson uses derivative information to make more informed correction to the current voltage estimate. The mismatch vector contains the difference between specified and calculated powers here, while the Jacobian contains the derivative of those power equations with respect to unknown voltage angles and magnitudes. The correction is obtained by solving a linear system involving the Jacobian. The updated voltages are then used to calculate a new mismatch here. The process continues until the mismatch is significantly small. The important idea is localization, local linearization. See, the original equations are nonlinear, no doubt, but around the current operating point, they can be approximated by linear relationship. So Newton-Raphson solves that local linear problem and then repeats the process at a new operating point. So when you look into the equation here, you got J here. This is a Jacobian matrix, partial derivative of every PEQ equations with respect to delta and V. Delta P and delta Q mismatch, the difference between specified power and power calculated from the current voltage. Yes. So Jacobian, a matrix of partial derivative recomputed or approximated at every iteration. This is the extra cost per step versus Gauss Seidel. So you got delta and delta V, the correction to apply to each bus angle and voltage found by solving the linear system above. Means when you go to the next iteration, you need to include this. I think you are quite aware of this, right? It's not something new. I'm trying to figure it out or explain. Well, as you can see here, when you look at the Newton-Raphson algorithm as a flow chart here, you have guess again voltage is 1.0, delta is equal to 0 at every unknown bus. Same like Gaussian, compute mismatch, delta P and delta Q specified, calculated power at every bus, build Jacobian matrix, partial derivatives of P and Q with respect to delta and V at the current guess. So solve and update. Solve for delta V, delta update. So the old delta becomes delta plus delta delta. V becomes V plus delta V. Okay. Then you get the new set of values for your P, for your Q, and everything. Okay. You may go up to multiple. Okay. If not converged, look back to compute mismatch with updated voltages. If converged, stop and report the final V at every bus. Okay. So the deck of 3 to 5 iteration statement is stated as a typical teaching illustrations. Okay. Because while teaching we cannot really go beyond 3 to 5. 5 iteration is too much. Uh, so it's not an universal guarantee actually. Actual iteration counts depends upon the system size, initialization, loading, tolerance, and formulation. But for understanding 3 to 5 is sufficient. So here we got an example, a simplified, it's a very simplified two-bus system. It's pretty easy thing, right? So you got a simplified setup, DC style approximation for hand calculations. See, bus 1 is a slack bus because you have values of V and delta 1 is equal to 0. What is modulus of V? What is modulus of V? Voltage magnitude. Delta, voltage angle. And then you got bus 2 is drawing around P to 100 megawatt and reactance of 0.01, base of 100 MVA. So P2 is equal to zero point 0.1 per unit. Using the DC approximation, PIG is equal to VI VJ multiplied by delta IG x find delta 2. Easy. See, consider the simplified two bus examples here. Okay. because bus 1 is the reference bus, right, at 1 per unit and 0 angle, and while bus 2 is represents the 100 megawatt load with 100 MVA base, the load is 1 per unit, and the line reactance is zero point 0.1 per unit. Therefore, using the simplified DC relationship, the magnitude of the angle difference is zero point 0.1 radians. Approximately, it will be. It is calculated here. You can see P2 is equal to minus 1, 1 delta 2 over 1. Therefore, 1 times 1 is minus 1. I mean, yeah, and 10 because divided by 0 0.1 you get minus 10 delta 2. Okay, P2 you have 0 0.1 here, right? Therefore, uh, P2 is equal to minus zero point 0.1 per power leaving the slack towards the load, right? And simplify. So if you simplify for delta 2, you get 0 0.1 radians, and that is 5.73 degrees. This calculation is deliberately simplified so that the relationship between the real power transfer and the angle difference can be seen directly without performing a complete AC iteration for you. So the important point is that this is not a full AC load flow solution. It is an hand calculation bridge to more complete Newton-Raphson formulation. The sign of the angle depends upon the chosen injection and flow convention. Okay, from where you are starting from where you are looking into the network. That all matters here. Okay, so the receiving bus angle is normally represented as negative relative to the slack reference always. So you can see here the 5.73 magnitude is retained. The sign of the load bus angle depends upon on the adapted injection flow convention under the common negative load injection conventions. So the receiving bus angle is normally negative relative to the slack bus reference because it is receiving and the slack bus is giving out. So if you have a look at the uh, comparison when to choose which methodology. So Gauss-Seidel Newton-Raphson makes a useful comparison. Gauss-Seidel has low computational effort per iteration and is easy to understand and implement, but it can require many iterations. When it comes to Newton-Raphson, it has had greater computational effort per iteration because the Jacobian matrix must be formed and correction equations solved. However, the method generally converges much faster when compares to Gauss-Seidel, and and near a well-behaved solution you can obtain and is widely used in practical power system analysis. So the comparison is therefore trade-off between uh, simplicity and convergence efficiency rather than uh, a statement that one method has no practical value. So what did we understand? Majoritively, we understood about the load flow analysis can now be summarized into one statement. Given a generation, demand, and the network model, calculate the electrical state. The bus clarification determines which quantities are known and which are unknown, right? The AC equation, the AC equations are non-linear because of voltage products and trigonometric angle relationships. Gauss-Seidel solves them through sequential substitution, while Newton-Raphson uses Jacobian to calculate the local corrections there, right? And this gives us an exactly what we need for a final part of this session. We know how to represent the physical network mathematically. The next question is how to make that physical network part of the optimization itself. That is where we have the fourth part, that is optimal power flow. See, uh, economic dispatch asked us how to allocate generation economically. Load flow asked what the network does for a specified allocation. So OPF asks both the questions at the same time. The optimization selects generator output and network control variables, while requiring the resulting electrical state to satisfy the AC power flow equations. generator limits, voltage limits, and line limits are included simultaneously. Because the network equations are nonlinear, OPF naturally belongs to the nonlinear optimization framework developed, what we developed in our part one. Okay. So when we look into the optimal power flow can be understood as economic dispatch with actual electric network placed inside the optimization. The objectives may be total generation cost, while equality constraints are full AC power flow equations. The inequality constraints represents the physical operating limits. These include a minimum and maximum generator outputs, voltage magnitude limits, and transmission line or branch flow limits. This is why OPF is best viewed as a union of concepts. Uh, Sorry. See, rather than as a complete new mathematical technique, the economics comes from economic dispatch, the physics comes from load flow, and solution framework comes from nonlinear optimizations. So when you look into a complete AC OPF problem, can be written with the generation cost objective, the real and reactive AC power balance equation, and the operating limits. So the generation variables are longer fixed inputs. They are decision variables. Uh, the voltage magnitude and angles are also part of the network state that must be consistent with the selected generation. The simultaneous treatment uh, the simultaneous treatment is what makes OPF substantially more difficult than a conventional load flow calculation. A load flow will solve the network for a fixed generation pattern. The OPF will search over possible generation and control settings while enforcing the network equation at a very feasible candidate. So when we look into the OPF as a union of three techniques, that is NPL, load flow, and economic dispatch structure. See, the structure of AC OPF can now be seen very clearly. See, we take Lagrange multiplier, KKT conditions, and nonlinear numerical methods from the part 1 of this class. From part 3, we take a full AC power flow equation. From economic dispatch, we take cost objective and generator operating limits. The three components are not simply placed beside one another here, they interact. Uh, a change in generator dispatch changes the network voltage state and line flows. So, a transmission limit can force generation away from the economically cheapest unit. So, a voltage constraint can alter reactive power dispatch and generator operating points. So, that interaction is precisely what makes OPF an important power system optimization problem. So, now the question is how can we solve optimal power flow? Yeah, in real practice. So, large scale OPF is solved numerically. Okay, the solver repeatedly evaluates the objective and constraints, obtains derivatives, informations, and calculates the correction until the solution satisfies the required feasibility and optimality conditions. So interior point method are particularly important for large constrained problems because they provide a systematic way of handling many inequality constraints. So the problem can contain large generator limit, voltage limit, and branch flow limits simultaneously. See, these are still important research issues like general AC OPF is non-convex, so a conventional nonlinear solver can converge to a local optimum. This is why convex relaxation such as semi-definite and second order cone approaches. So global optimization methods and other advanced approaches remains uh, active research areas. Research note general AC OPFC is non convex. Numerical convergence to a feasible stationary point does not does not by itself establish a goal optimally. When you look into the uh, previous sessions DC OPF and today's sessions AC OPF, as you can see, they differ mainly in network model, right? DCOPF linearizes the relationship between the power transfer and voltage angles and normally neglects right, or simplifies several AC effects. The result is much faster linear optimization problem. But when you come to ACOPFC, it retains the voltage magnitudes, reactive power, and full AC network relationship. It therefore provides a more physically complete representation, but the computational problem is non-linear and generally more difficult. Therefore, the engineering choice it completely depends on the purpose of the study here. Linearized formulations are extremely useful for fast dispatch and large scale screening, right? While full AC formulation is important when voltage, uh, reactive power losses, and detailed network constraints matter to us. If you want to have a small case study, optimal power flow inside a real energy management system, you can see here this is from a textbook formula to control room software. In real energy management system, these calculations are not isolated academic exercises. What happens there is measurements from the grid are continuously collected through systems such as SCADA. A state estimator processes those measurements to obtain an estimate of permanent network state, and load flow and optimization calculations then use that state to assess network conditions and determine feasible operating decisions. When contingency requirements are included, the problem becomes security constrained optimal power flows, in which the operating points must satisfy additional security requirements. This provides the practical connection between the mathematics of today's lecture and control room operation. The sample concepts of nonlinear equations, network states, constraints, and optimization are embedded inside a large scale of operational softwares. Finally, we are reached the point where we can have a look of OPF. OPF can therefore be summarized as an economic objective constrained by an actual AC network, physics, and by engineering operating limits. The objective is normally a generation cost, the equality constraint, or the AC power flow equation, and inequalities are generators, voltage, and transmission limits. See, DC OPF provides a linearized and computational efficient alternatives. AC OPF retains the full AC formulation and therefore gives a more detailed physical representation. In practical power system operations, OPF forms a part of broader chain involving measurements, state estimation, network analysis, contingency assessment, and dispatch decisions also. So, when we minimize f is equal to summation, here you have the objective. This is unchanged from session 1, right? So what did we learn from this entire session 3? The session 3 now, it can be viewed as one of a continuous progression, like we started from NLP, removed the linearity restrictions there, and allowed the true nonlinear cost functions to be retained. The Lagrange multiplier produced the equal incremental cost conditions, and KKT condition provided the framework for active operating limits. Dynamic programming introduced the different dimensions, decisions that evolved through the stages. Load flow then returned to the physical network and calculated the voltage, state, and power flow associated with the specified injections. Finally, OPF united the economic objectives, network equations, and operating constraints. Uh, Nothing from previous session was discarded here. Instead, each mathematical idea became one component of a more complete power system model. every unconstrained generator marginally cost equals to lambda, right? The system marginal cost, the same idea as LP duality shadow price. So quick references, this is a formula sheet, this is very important, I'm gonna share it across with you guys. You have Lagrange's equation where you have the inclusion of the Lagrange's module, and you have KKT stationarity, complementary slackness, right? Equal incremental cost, Bellman's recursion equation, AC power flow. This is only for real power flow. Newton-Raphson updates, right? Optimized power flow conditions where you have minimized power, and these are few numerical problems you can work on. In session 4 we can look into economic load dispatch in the upcoming class. uh, do you have any doubts? Excuse me.
Sir.
uh, Anything further discussion you would like to have?